Hello guys, welcome back, and we have started a discussion on finite impulse response filter. So today we'll be starting another series for finite impulse response filter design. Now this thing I have divided in 8 small lectures. So I'll try to restrict that each lecture within 15 minutes. So 10 to 15 minutes will be the duration of each of the lecture. Now the entire thing has been divided into 3 different methods of FIR filter design. So most popular one is the window method of FIR filter design, and then frequency sampling method of FIR filter design, and lastly the Fourier series method of FIR filter design. So here we shall take 4 small lectures for window method, then 2 each for frequency sampling method and Fourier series method of FIR filter design. So under window method, in this lecture we'll cover the general description of window method, and rectangular window we'll discuss in particular. There are other windows also, so subsequently we'll discuss that in the next lecture, followed by what are the steps we need to follow for designing the window, and finally we'll take one numerical, we'll solve that numerical, and we'll see how FIR filter can be designed. So coming to the general description of window method, many book you will find that they are starting with the desired frequency response, but I personally feel that before going for the desired frequency response, we must know that what is impulse response, that is in the time domain. So if you have an LTI system, and suppose this is a filter, because FIR filter is LTI system that we have seen in our first lecture. So here you have some impulse response, and we are calling this as desired impulse response. Why it is desired? Because desired means what do we want? What do we want? So that is giving us the desired. So that means we are giving some input x of n and we are getting some output y of n. Now if this desired response is known and it is infinite duration, okay, so directly we can go for IIR filter design, or we have seen that there are advantages of FIR filter over IIR filter. So considering the stability and the linear phase, we may go for finite impulse response. Now since it is infinite duration, so we have to convert it to a finite duration. So how we can do it? So we shall use a process called truncation. And for truncation we use a function which we call as the window function. So basically we are windowing of this infinite duration sequence and making it a finite one. So we can say that h of n, the impulse response of our FIR filter, will be nothing but hd of n within a finite duration, say n1 to n2, and here it is 0 elsewhere. Okay, so how do we do it? As I have mentioned, the process is called truncation with the help of a function called window function. So basically we are defining some window function, say w, okay, w of n, as say let us take the simplest of one, rectangular window. So we define that w of n as say 1 within the range n1 to n2 and 0 otherwise or elsewhere. Okay, so now if I multiply this one with this one, then what I'll get, h of n I'll get as h d of n into w r of n. So this entire thing is the time domain, and what we have got is the actual impulse response of the FIR filter that is to be designed. So here we are taking help of another function, what we are naming as window function, to make the desired impulse response a finite one. Now if you see, this is a multiplication in the time domain. So multiplication in time domain will result in what? Multiplication in time domain will result in convolution in the frequency domain, right? So things will get convolved. So if we have hd of e power j omega as the transformed dtft of hd of n and wr of e power j omega, then this will be the convolution, and that is how we will get h of e power j omega in the frequency domain. So let us have some more relations. H d of e power j omega, how it is given. Now we are coming to the desired frequency response, h d of e power j omega. So that we shall get as summation over n equal to minus infinity to plus infinity h d of n e power minus j omega n. I believe you can identify that this equation is nothing but the dtft, and similarly from here what we get, h d of n by applying the inverse dtft, so that is equal to 1 by 2 pi integration minus infinity to plus infinity h d of e power j omega n d omega. So these are the relations, how h d of e power j omega and h d of n, how they are related. So with this thing we shall proceed further, and same thing is applicable for wn also. wr of n will get from the inverse transform, and wr of e power j omega will get from the forward transform. Okay, so I am leaving it to you, so you will be able to do it of your own, I believe. So now if you now look into it, that we have seen how we are getting h of n. We are getting h d of n multiply wr of n. So r stands for rectangular. For our convenience we are considering this is a rectangular window. Okay, so similarly we will get wh of e power j omega. So this will lead convolution, right? Convolution in the frequency domain. So h of e power j omega, that is equal to h d of e power j omega convolution wr of e power j omega. Okay, so that means if we mathematically put it, we will get 1 by 2 pi integration minus pi to pi h d of e power j omega h d of e power j theta, rather w of wr, in this case you can write wr of e power j omega minus theta d theta. So whenever you will be deriving it in exams, it will be better always you give the equation number. For simplicity I am not numbering these things, but it is always better, it's a good habit to put equation numbers. And one small correction you make here, it is not minus infinity to infinity, it is rather minus pi to pi. Okay, so this correction you make. Okay, so now if we look into it graphically, what do we observe? Suppose the window function WR of n. So as I said, it is a rectangular window, so it will be a rectangular pulse. So what we get, this is, suppose this is the window, finite duration window ranging from minus n minus 1 by 2 to plus n minus 1 by 2, or previously whatever we have used, that n1 to n2. Now n1 can be from 0 to n minus 1, it may be any duration. Okay, so for the time being let us consider it like this. So if we perform the DTFT on it, then we shall get a sinc function. So this kind of thing we will get. Okay, so this kind of things we will get. So this is WR of e power j omega. So this thing will be getting. So this is called the main lobe and lobe BE. Okay, and these are the side lobes. So side lobes, which are very much undesired thing. Side lobes are very much undesired thing, and that will lead to some problem. Later on we will see that. So here now, as we have seen that HD of e power j omega, how do we write it, or how do we draw it? The desired frequency response, that means the ideal case. So HD of e power j omega, so this is my ideal, and the total frequency for digital frequency we know that will range from minus pi to plus pi. So suppose this is my cutoff frequency, omega c and minus omega c. So if it is a low pass filter, then the desired frequency response will be like this. This is what is our desired frequency response. And we have seen earlier that our window function, which is nothing but a sinc function. So window function is a sinc function, so that is WR of e power j omega. So this much will be getting something like this. Okay, and so this thing will be getting, and if we shift it by theta unit, that is WR of e power j omega minus theta. Okay, so that is as per the definition. Earlier we have seen that definition. So as per this definition of convolution, now these two spectrum will convolve with each other. So we have to perform convolution. So they'll be convolving with each other. So that means we'll have shifting of the spectrum. So something like this we may get. We may get something like this. Okay, and here also we'll be getting one sort of main lobe. So this thing will be getting, and if we superimpose this here, that is our desired frequency response. This is the desired frequency response, that is hd of e power j omega. So will be resulting in to h of e power j omega. So this is h of e power j omega. So what we will get here? Okay, so very interesting one. So we'll be getting some small ripples here, and then we'll be getting something like this. Similarly here also we'll be getting something like this. Okay, so it will be like this. Okay, so this is minus omega c, this is plus omega c, and it will go up to pi, and this side will go up to minus pi. So this is what h of e power j omega, and that we need to design. Okay, so it looks very easy, and few things only we need to take care of. Now if we see the rectangular window, so after this general discussion, okay, so a few things we need to understand, that desirable window characteristics. So desirable window characteristics is saying that small main lobe width. So this is the main lobe width. Okay, this should be main lobe width should be small. Main lobe width should be small, so that frequency response will be better if the total energy is concentrated within a small duration, and side lobe of the frequency response should decrease rapidly. So this should die down as soon as possible. The window functions are designed with a view to reduce ripple rate. So ripple rate, here you have the ripples in the passband. So ripple rate, which is defined as the ratio of maximum side lobe amplitude to the main lobe amplitude. So maximum side lobe amplitude, so this is the maximum side lobe amplitude to main lobe amplitude. So this ratio defines this ripple, and this ripple ratio decides passband and stop band ripples. So ripple in the passband and ripple in the stop band, these things are decided by this particular ratio. And the drawback of using window is that it introduces the transition band in frequency response, so which is quite natural in any filter whenever we are designing. So this is the ideal one, okay, desired or ideal one, but this we can get with infinite parameters. But in practical, whatever we'll get, there is a roll off. So this is roll off. So for analog filters, we say that the degree of the filter, or rather order of the filter, decides the roll off, and in this case the duration or the length of the window function that decides the roll off or window function, or you can say that FIR filter h of n, length of h of n will decide the roll off. So naturally you can say this is a disadvantage or it's a limitation, but it is valid for all kind of filters. Now coming to the rectangular window. So earlier also we have defined the rectangular window, and how does it look like, that we have seen that rectangular window, WR, we use this R for defining the rectangular window. So it will be something like this, okay, and it is ranging from minus n minus 1 by 2 to plus n minus 1 by 2, and some cases we may also see that this is ranging from 0 to n minus 2, 0 to n minus 1, 0 to n minus 1. So this thing is also valid. Okay, so mathematically we can define that WR of n is 1 for minus n minus 1 by 2 to n minus 1 by 2 and 0 otherwise. Okay, so this is the frequency response of rectangular window, and we can find its Fourier transform version WR of e power j omega. So that is equal to summation. So since here it is getting limited between n minus 1 by 2 to plus n minus 1 by 2, so that limit will utilize n minus 1 by 2, and so now it is 1, we have it 1. So WR of n, that value is 1, so we can say 1 into e power j omega n minus j omega n. Okay, 1 e power minus j omega n. So that will lead us, if we solve this, that will lead us to WR e power j omega, that is equal to sine omega n by 2 divided by sine omega by 2. So that is basically a sinc function. So sinc function that will lead us to this kind of response, and this width for rectangular window, this width will be 4 pi by n. So this is a standard width. So WR of e power j omega. Okay, so now this is the simplest of all windows. Rectangular window is the simplest of all window, and it has the drawback that there is a overshoot and leakage introduced in the frequency response. So overshoot and leakage. So whenever we'll be designing the FIR filter, so it may so happen that we may get some overshoots like this. Okay, this kind of response we may get, or also we may get it something like this. So this kind of thing also we may get. Okay, so this thing is called Gibbs phenomenon. This is called Gibbs phenomenon, and this is the greatest limitation of rectangular window. So that is why rectangular window is seldom used in practical purposes. Now to reduce this side lobe effect, what we need to do, that we must consider that alternate window sequence, and which is having the spectrum exhibiting smaller side lobes. And how we can get that? Instead of using this kind of sequence for window function, this kind of sequence, we may use some tapped type of sequence. So this kind of sequence will be a better one. So based on that, there are different kind of windows like triangular window, then we have Hamming window, okay, then we have Henning window, then we have Blackman window, and we have Kaiser window. Okay, so these all windows we shall be discussing in our next lecture. So that is are the other windows and all of them have some advantages, some limitations. Okay, so and that also will be summarizing later on. And rectangular window, another thing is that the minimum stop band attenuation, minimum stop band attenuation for rectangular window is minus 21 dB. So if we are designing some rectangular window where we need this thing to be satisfied, that minus 21 dB, then we can go for rectangular window. However, rectangular window, as I said, we seldom use for the practical purposes because of this Gibbs phenomenon. Okay, so these are the references that I have used to prepare this lecture. I request you to go through these books. These are extremely good books, and you can explore these books for further studies. So thank you very much for join me on the next part, where we will be discussing about the other windows. Thank you once again.